manufacturing industry. And since joining here, I've focused on agriculture, food tech, and synthetic biology. But looking forward to discussing something completely different today and talking about the energy grid. So with that, I'll go in order of my screen. Tim, do you want to introduce yourself quickly?
Sure. I'm excited to be here. Tim Heidel. I'm the Chief Technology Officer at Veer, which is a 2.5-year-old startup focusing on next generation superconducting based transmission lines that can fit 5 times the amount of power through the same right-of-way space relative to conventional conductors. So transmission is something that is very near and dear to our heart, of course, and super important topic. Excited to be here.
And next, Liza.
Hi, I'm Liza Reed. I'm the research manager for electricity transmission policy at Niskanen Center, a DC-based think tank, and I'm a grid fellow at Prime Movers Lab. So really excited to dig into the tech side of the discussion today.
Thanks, Liza. And last but not least, Anna.
Hi, I'm Anna Brockway. Thank you so much for having me. I'm happy to be here today. So I'm currently an advisor at Southern California Edison on climate adaptation and resilience planning for electricity systems. I just about 3 months ago finished a PhD at UC Berkeley in energy and resources, where I also got a master's degree in electrical engineering. And my graduate work was really focused on kind of one foot in power systems engineering in terms of understanding the technical needs of our systems, and then one foot in policy and decision making for the future of electric power systems, focused on distribution grid and distributed energy resources, as well as climate adaptation. So very happy to be here today. I do need to note that I'm not speaking for the utility in any way. I couldn't, even if I wanted to, since I've only been there for 3 months and I'm still learning a lot. But thank you for having me.
Absolutely. Thanks for joining us, and duly noted, speaking for yourself. To kick off, I want to start with.
Oh, Brad, do you mind if I jump in real quick? I forgot to do housekeeping at the beginning.
Yes, absolutely. Go ahead.
All right, so sorry about that, everyone. So just to be clear, we like to be respectful of everyone's time. We'll keep this to 1 hour, so we'll end on the hour. And please use the Q&A and chat session. We encourage the audience to field questions live, and we'll filter them in. We monitor them throughout the webinar. And yeah, that's it. Thank you, everyone, for joining again. And let's go, Brad.
Thanks, Liz. So to start, I want to begin by understanding, what does the grid look like today? And I'll qualify here that I really mean in the US, but maybe later we can talk about what does the grid look like in some other countries. So what does the grid look like today? And how are the demands on the grid changing as we move to a more electric economy, and as things like climate change change kind of the environment that the grid operates in?
Well, I'll dive in with a little electricity grid 101. Our grid is a couple 100,000 miles of transmission lines, where when we think about transmission, we're talking about 100 kilovolts or more. Anything lower than that we call distribution. So transmission is sort of this high capacity. You're moving over long distances. The higher the voltage, sort of the longer distance you can move it over. And predominantly AC. I don't know how much we want to get into the tech of AC/DC. I think we'll probably dive in a little bit as we discuss, but predominantly called alternating current. We've got a couple 100,000 miles, and it's largely connected, but not completely connected. So we have a couple of different grids. There's an Eastern interconnection and a Western interconnection. And sort of importantly for how the demands are changing, this grid has been built over 100 years. And when we started building electricity, it was just going one way. You were generating and you were sending it to a load. And now we're finding that that's changing a lot, right? Electricity flows wherever the least resistance is. You can share power in different directions. When you have a grid, when you have hundreds of thousands of miles of electricity spanning an entire country, there's not just one way, there's not just one path. And so we see the demands changing and how we manage that flow, how we think about where generation is coming from, right? We're not just seeing giant power plants, we're seeing more local power plants, or even rooftop solar, right? And so how do we think about how that power should flow, and who's managing it and how it's being managed, are some of sort of the big ideas about what we're.
Thanks, Liza.
I'll
Yeah.
dive in a little bit and just give a perspective on how things are changing as well. And I think, the grid's poised to need to grow pretty significantly. The total electricity use is going to grow pretty significantly if we get real serious about decarbonization, right? From electric vehicles to electrification of heating for buildings, to electrification of industrial processes, right? Like electrification is one of the simpler pathways to decarbonize a whole lot of our end uses. But every single one of those new end uses that we're going to increase requires more energy, and that requires more capacity. And so you're going to see that grid grow even more important over the next several decades. I think that just looking at the grid today, right, we should acknowledge that this is a system that operates 24/7 in a safety critical applications. It's an absolute marvel of engineering that has been built over the last 100 years, and nobody's willing to give up any of that reliability and safety as we move forward. And so that's the sort of thing that colors everything that you think about as you think about that future expansion.
Yeah, to add on that, absolutely agree with everything that has been said. I think there's just widespread agreement that there's going to need to be much greater demands on the electricity system due to electrification. A lot of those demands are going to be occurring throughout the distribution system, at customers' homes, at businesses, as people electrify, get electric vehicles, that kind of thing. It's the way that we plan for the grid right now is really going to need to change. So currently, the planning models that are used in the industry in order to essentially invest in new infrastructure, plan for increased demands, a lot of those models are almost entirely based on historical assumptions about kind of the rate of demand growth, about the changing, about climate conditions, and all of those things are going to need to be changing. And so in thinking about what we do for the future, we need to think about new technologies that can enable the grid to work in new ways. We also need to think about how we in the industry really even understand what kind of conditions we are planning for and how those are baked into industry approaches to plan for a different future.
All right, I think that's a great way to transition to one of the questions that is top of mind for me. So you mentioned, how the grid was historically planned in the past and what the requirements were and what it needs to look like in the future. So it sounds like we're going to be needing to build more, right? And I think I could geek out about the technologies all day and we'll definitely get there. But first, I'm curious, what are the regulatory challenges and hurdles that we'll face in order to build the grid of the future?
I'll kick us off again since this is my, this is my full-time job is in regulations and policy. So one of the regulatory challenges is that locus of control, right? So when we think about transmission lines, these are usually in the state purview. So a state public utility commission is deciding what transmission lines are being built. There's a couple of challenges with this when we think about a national electricity system. One of them is that the state almost always legally has to consider only the impacts for the state. But if you've got a transmission line that is impacting multiple states and is overall providing more value to other states, you've now got a really difficult sort of federalism tension here, right? Where you've got a regionally important project that a state is maybe not incentivized or interested in building. And so that is a major regulatory challenge in just getting lines built. Tied to that, Tim was talking about we're running 24/7, absolutely critical infrastructure. There's also that responsibility where understandably utilities, it is literally on the utility to be responsible for this reliability, right? For ensuring that the grid stays on. But what that can result in is also sort of a more reluctant approach to incorporating new technologies or thinking about how we're using the grid differently, right? Thinking about how we can let on storage and solar, right? How we can let on sort of distributed resources and even deploying the technology to use that. We've got systems that are running Windows 95 or earlier, right? And how are we managing to incorporate sort of fast moving internet connected power electronics that can manage flow on the system. So it's a little bit of a technical challenge in there too, but these regulatory barriers of regulated utilities, right, who have existing legislative authority at the state level, lack of significant federal authority, and really kind of a vast unknown for any new entrant to try to navigate how they're going to get a foothold and then even a market share.
The thing I'll add is unfortunately, transmission infrastructure generally isn't very popular. There's tends to be a lot of public opposition, especially to brand new right-of-ways that are cutting through, any pristine area or any greenfield project. I mean, greenfield infrastructure of any type always faces opposition, but really tall steel towers seems to really get a lot of focus. And so it's really, really hard to build new infrastructure. And that is a layer that really enters a lot of siting, permitting, and regulatory processes, is just how far against new infrastructure many folks are.
Yeah, and I think that was something that, sorry, Anna, I cut you off, but just to talk about a little bit later, whether or not we're going to go underground in the future. But Anna, please finish your thought.
Well, I was just going to add that in thinking about how to plan for this future, part of working within this kind of heavily regulated landscape of a critical infrastructure sector is really also being careful in terms of changing, how, and Liza alluded to this, kind of how we plan for the challenges that we to face from here on out. And there are relationships in terms of what the utility has control over, what the regulator has control over, what kind of models and decision-making tools are being used. And some of those are being prescribed by a regulator, some of those are being developed by utilities, some of those are industry standards. And in some cases, utilities are kind of trying to figure out a new landscape before an industry standard is established, when we're talking about things like significantly increased electrification or climate change. And so it's kind of the roles of those different participants in this space, but then it's also thinking through kind of what is a planning system that actually makes sense in terms of understanding what are the biggest challenges that we're going to need to adapt to, and how do we code them into the ways that we are making decisions today.
Yeah, definitely. I sort of wonder about that as well, especially as we're just going to have more use and more different times, right? So we're switching to more and more renewables, which generate during certain times of the day or certain seasons, right? How much of the future is going to be upgrading grid infrastructure and materials for transmission versus the storage piece? So we might be switching a little bit to tech soon, but that's my bias. Tim, would you mind talking a little bit more about the applications and things you're working on at Veer?
Yeah, so at Veer, we're focused on developing whole system approaches to the next generation of superconducting based transmission lines. So the novel innovation we started with is a cooling approach that allows you to deploy superconducting based lines over long distance. Historically, high temperature superconductors have really been focused on urban core, underground, relatively short distance applications. There's a whole host of reasons why that's been the case. We think to have a really big impact, we need to be able to build lines that are tens, if not hundreds of kilometers long, and that needs new technology. Our focus right now is overhead. Ultimately, we will also build underground and subsea variants of the technology, but today, the vast majority of transmission that's deployed in the world is overhead and has been historically. That's what we know how to engineer. That's what is routine, right? I think anytime you start talking about underground, especially over long distance, people get really nervous, right? Both because the perception of very high cost, it absolutely has been higher cost in the past, but also the perception of risk, that you don't really know what you're going to encounter until you actually start construction. And that risk adds to project risk far later than you really want to have project risk. And so there's a great comfort in overhead. One of the things we focus a lot on is reusing existing right-of-ways and being able to upgrade the capacity within existing right-of-ways where you already have siting and permitting approvals, and where all of your neighbors are already used to having a transmission line there, right? They've been looking at a transmission line for decades. And so upgrading it is going to face relatively less opposition. And indeed, we see that in a lot of the data that we've looked at. The times for reconductoring or rebuilding an existing right-of-ways is a much shorter process. You're talking about years shorter, 5 years, 6 years, 8 years shorter than the prospect of building a brand new high capacity, high voltage line in a new right-of-way. And so we think that can accelerate deployment. That's just one option you have for really building capacity a whole lot faster, which we think is really important in the future.
Great, thank you. I have a couple of follow-up questions. One is, I know what you mean by high temperature. Can you define for the audience? And then two is, will your materials help reduce the risk of, transmission-induced wildfires? So
It's a good question. So yeah, so high temperature in our context is not really high temperature. It's 77 Kelvin. It's about -200 degrees. It's the temperature of liquid nitrogen. And so this is high temperature relative to previous generations of superconducting materials that have been just demonstrated over the last couple decades, but it's still quite low temperatures. And so the challenge with a system like ours is we do need active cryogenic cooling. We flow liquid nitrogen through pipes that keep our conductor cool. That has concerns. It has risks associated with it that we have to engineer carefully, and we're confident we're going to solve those risks. It also brings benefits. One of the benefits that is a pretty big benefit of ours is our capacity of our transmission lines don't vary with environmental conditions. So historically, as you get hot days with no wind, existing conductors start to heat up, and you have to derate them to be able to operate safely. Because we have an active cooling system, we don't end up dealing with a lot of that. In terms of fire risk, so there's lots of ways you can reduce and mitigate fire risk. There's a tremendous amount of effort on preventing and mitigating wildfires. Obviously, one strategy that a lot of folks are looking at is undergrounding. So remove the infrastructure from the environment, don't have the ability for vegetation and failures to come into contact with live conductors. What's really hard when you can't underground is historically you have not been able to build what are called covered or insulated conductors in transmission. So transmission lines that you see on large steel towers out in the world today use bare conductors. The conductor that you see is actually at the high voltage, so that may be a couple 100,000 volts, and you're using the air surrounding the transmission conductor as your dielectric insulator. That's what allows you to operate at high voltage relative to ground. But what that means is if you get a short between the conductor and ground, a tree or vegetation of some sort, that can spark and start a wildfire. Historically, the simple answer you might have for how do you solve that is to put a big insulator around the conductor. Well, in theory, you could do that, but that insulator now traps heat into the conductor. It also adds significant weight. And so now you have to upgrade all of your towers and you've got to upgrade all of your other supporting infrastructure, and it just becomes very, very expensive. And when you trap that heat inside the conductor, it heats up even faster and you need to derate it. In our system with an active coolant, there may actually be opportunities that we'd like to look at down the road. We haven't started actually engineering that today to add insulation on the outer surface because we're not relying on heat removal by the environment.
great, thank you. Anna, I see you came off mute. Do you have something you want to add on the wildfire side?
I think I've just been off mute. I should probably mute myself when I'm not talking. Well, it's really interesting to hear about the technology that Tim is working on. I think this brings up, to me, this kind of brings up one of the regulatory challenges that you mentioned, which is in terms of putting plans in place to deploy technologies like this. Utilities are operating on like 3 to 5 year funding cycles where, they submit kind of their scope of investments to a Public Utilities Commission that can, with the justification of these are the investments we want to make, and this is how this will improve or sustain reliability, safety, cost effectiveness for the customers that the utility serves. And the Public Utilities Commission will, approve or reject or modify some of those investments going forward. And then that is kind of the amount of money that the utility has to work with for maybe up to 5 years. And so deploying technologies like this throughout a utility system has to kind of clear those regulatory hurdles. And it also has to do this on kind of a specific, kind of planning cycle. And so that's just, part of, I think, working in this industry and trying to incorporate kind of new promising technologies in that process. There kind of are some of these additional regulatory challenges to deal with.
When we think about new technologies and rolling them out, I think maybe it makes sense to take a step back and think about what is the current business model that the grid operates on. And Tim, maybe if you have thoughts on this, like how do you get into that business model and create value for yourself?
Yeah, so there really isn't a single business model in the transmission space. There's actually a large diversity of different organizations that build transmission for different purposes, right? So obviously you've got traditional regulated utilities that build a tremendous amount of transmission every year on a routine basis, but you also have generation developers who are trying to access the grid and building transmission in order to build into the access of the grid. Increasingly, we're seeing industrial customers, data center owners also take on a portion of that transmission development work. And then there are competitive independent transmission companies or merchant transmission companies. The term that's used varies regionally and internationally. And you're actually seeing a lot more competitive transmission development internationally today than what you've seen historically. And so the specifics of the business model as well as the timing really varies depending on all of those different pieces. Unfortunately, this is not a simple market. This is a very complex market. It is not an easy one to break into. And so you do have to get creative in terms of the partnerships that you form, the timelines that you can tolerate, and then thinking about, how do you get directly involved in helping people deploy projects? And how much of that project work do you actually take on, as opposed to the other end of the spectrum, which could be, an equipment sales type business model, which is harder to really make at least the math work for a venture capital investment, for example.
I'll add to that, Tim. I think you're absolutely right. It is far too complex. There's too many business models. There's also the different landscape for software solutions versus hardware solutions, right? Where hardware solutions have ostensibly a little bit more access, and that they could work with a merchant developer, they could work with an investor-owned utility, right? It is an attempt to sort of plug in, and I'm not suggesting that it's easy to plug in with a new technology, but a software solution, the actual management of the grid flow is fairly concentrated, right? Regional transmission organizations and major utilities, sort of incumbent utilities, right? The merchant utility, the merchant developer is building a line and operationally managing it, but the grid flow itself, where we need these software solutions, I'd say is a much narrower set of companies. Would you agree, Tim?
Yeah, I would say there's different barriers that a lot of the software companies can face. Concentration of the market size in some cases. That one of the nice things that we've seen is that a lot of software solutions can be stood up and piloted in parallel. They're making decisions, they're telling you what they would do, but they're not actually pushing the button and making a decision. They're more decision support frameworks, and that gives people a lot more comfort to get experience with those solutions running in real time, running in parallel to the real grid for some time before they flip over and start using them. It's a lot harder to get there with a hardware solution, right? Can we really deploy that capital and run in parallel where we're not actually solving a problem for some time?
Liza, I want to come back to you here. I'll set this question up as a hypothesis, and you can tell me if I'm right or wrong. The grid historically has had centralized production and decentralized consumption. And I think with renewables, we're shifting to a system where production is more decentralized. What needs to exist in order to enable that, or am I making a faulty assumption there?
No, I'd say that's a fair high-level characterization. And, there's actually a couple of different models for how we think about what needs to happen, which also makes this a fascinating investment policy research technology space, right? On the one hand, there is there's a growing chorus around this idea of something called a macro grid, where you would create an overlay over the United States so that you can consolidate, even though you don't have, to your point, you don't have necessarily as centralized power, you could do it on a macro grid level, right? You can take solar and wind and geothermal and storage and ship it to wherever it's needed across the country, since you're not building a gas or coal plant just outside a major city, right? So that's one sort of extreme direction, and that's based on high voltage direct current. That's a lot of sort of power electronics and different uses of right-of-way, as Tim was mentioning. On the other end, there's the sort of extreme level of distributed, right, where you're looking at highly local power, where you're talking about microgrids, right, and you're talking about even two-way power flow right at the meter, right, which we really don't have, right? I mean, we're starting to see that, right? That's what net metering conversations are about. So clearly our audience, I'm sure, is familiar with that. But when we start thinking about it at scale, that's just a completely different way to think about the grid, right? So there's sort of this bottoms up and tops down, and arguably we need both, really, because the local solutions are incredibly important for getting the most out of our infrastructure, minimizing our need for new rights of way, like Tim was saying, right, and enabling sort of local resilience. But the ability to ship power across long distances is crucially important for things like weather resilience, right? When what we saw happen in Texas last winter or 2 winters ago now, right? Texas needed power from elsewhere, right? And rooftop solar wasn't going to be the answer to what Texas needed, right? They needed to bring in power. And so we really see sort of both directions needing sort of additional focus and investment, but that macro grid isn't one way, right? Those transmission lines can send power in both directions, right? They're pulling in from many power plants and moving it around the country.
I actually wanted to jump in on that one, and this can go to anyone. So my understanding with Texas is that they sort of have their own independent grid infrastructure, right? And you mentioned like there's an eastern grid and a western grid at the top of the hour when we were introducing the grid, right? And there's sort of these intermediaries in between. What would it take to create a national grid to move an electron generated in the desert in California or Arizona over to somewhere like Texas?
Couple $1 trillion.
Only that. So, you know.
Tim, do you have a more sophisticated answer?
It's really hard. I mean, the history and the politics of it is going to be really hard no matter what. You know, long distance DC lines that are fully controllable, that are a source in one area and a sink in another area, probably is where you start. And beefing up some of the interconnections that exist between those interconnections today, possibly with longer distance lines to really deliver power strategically into specific locations. That all seems like it's feasible and could be done largely within the existing models that we have. Creating that high level sort of macro grid overlay, there's a bunch of proposals that have been floated on how you would think about setting that up from a regulatory perspective, how you would operate that, how you would maintain it. Right? A lot of those models tend to draw back to inspiration on the national highway system. I think it's anybody's guess what emerges at this point, and how long that might take. I don't know. Certainly, we need a lot more capacity, no matter what model we ultimately choose for that.
Yeah, I think the national highway system metaphors, I think I completely agree. That is the metaphor that folks use the most. There's a couple of challenges with it, is that in terms of folks accepting it, to Tim's earlier point about accepting infrastructure, you're using a road in a way that you're not using an electricity line. You don't see your electrons, you're not moving. And while I'm sure there is some traffic engineer who will tell me that this is not correct, for the most part, a traffic jam in New York is not going to cause a traffic jam in Texas, right? And a national grid actually does need a national sort of oversight and monitoring, as Tim was saying, right? That we don't need for a federal highway system. And, we've seen a lot change in policies in the last 12 months, even since the bipartisan infrastructure law from November, and then potentially rumors of future legislation to shift sort of to create some federal authority. Because certainly if you're going to create a national system, that requires a national focus and a national plan, which we don't have right now.
Yeah, I think what we mean by kind of regional coordination is also starting to change. In a lot of planning models, there have been assumptions that were made about, being able to import power from other regions where maybe you have a demand spike and you have reduced generating capacity in your own region. And as we're seeing right now, with kind of widespread regional heat waves, for example, all of your region that you had previously thought of your region that you could import power from might be experiencing shortages. And so maybe that's carrying power from longer distances. Maybe that's thinking in a different way about how we actually build generation that can serve load more locally. But there's certainly a need for thinking more broadly about what does it mean to move power around and share those resources.
Great. We have a couple of questions here on the technology side that we haven't touched on yet. One that I'm a bit curious about is, what are the national security risks associated with grid, right? Where it is state of things today and in the future as we build towards more and more renewables and this, sort of more tightly woven infrastructure?
Well, I'll jump in with a couple perspectives, which are really based on past jobs and past life throughout my career. I've spent a little bit of time focusing on cybersecurity and a little bit of time focusing on resiliency in other areas. And I think resiliency has certainly become a much, much bigger focus in the last decade or so as a major new requirement. And that has been a real shift in thinking towards making sure you have the redundancy, making sure you have the recoverability in the face of natural disasters has been the big one that people have really been focusing on. But I think there's also been a tremendous amount of work on improving cybersecurity protections, as well as response capability, right? And that's one that is going to come, and it's out there. More capacity and more, dare I say, hardware, right, in place allows you to have more flexibility and resiliency around any sort of disaster scenario that you might have. And unfortunately, that may come across as sounding like you want to overbuild and you want to build too much, and it's not at all what I'm advocating. But I think the trend line is very clear in that sort of thing.
I think it's important to understand the difference between reliability and resilience too. And one of the major differences is that reliability has a definition and has a body that oversees it. So Congress established the North American Electric Reliability Council as the authority that determines what's reliable for the grid and says that FERC must ensure that we have a reliable grid. The conversations around resilience are in development, right? The Federal Energy Regulatory Commission told NERC, so it's FERC and NERC, it's a little ridiculous, told the North American Electric Reliability Council, NERC, that they had to come up with a resilience standard, but that was last year, right? So we're still seeing a long timeline in sort of stakeholder agreement with that and understanding how that's going to be interpreted. One of the things, we talked earlier about grid capabilities, and one that I want to make sure I bring up here is black start, right? So that's one of the lines of where you go from reliability to resilience. Is reliability is when you can keep the lights on, and resilience is when you couldn't keep the lights on and you need to figure out how to get back to working. If the grid actually goes down, which didn't happen in Winter Storm Uri, but did happen right in 2003 in the blackout, you need to physically restart it. That's called a black start, right? Starting from a blackout is called a black start. It's quite complex. It's literally a complicated process because the power always has to be consumed instantly. So you have to turn on a plant and turn on a load and sort of match them and slowly build up the entire grid. That's why it took days to recover from the 2003 blackout. That's even harder with things like alternating current technology. There are systems like direct current, especially the latest instantiation of direct current technology, that can allow that black start more easily, I should say. But again, without a definition of resilience that is sort of quantifiable and able to be made an economic necessity for utilities, then shifting to incorporate these technologies is a little bit harder.
That was fascinating. Thank you for sharing. So we've got a couple of questions here. Maybe talking a little bit, one for Anna. Can you talk a little bit about like sort of like demand side management and what you're seeing there and what you think we'll be seeing in the future?
Yeah, absolutely. So one of my final kind of work products in my graduate work was actually taking a pretty kind of detailed quantitative technical study of the grid capacity remaining on the distribution circuits of Pacific Gas and Electric. And so PG&E is the largest utility in California. It serves pretty much all of Northern California, and is seeing significant increased new demands on its grid due to electrification of EVs and adoption of residential heating. And so what we did in this work was essentially look at where on their circuits there is still actually room to accommodate new load, and then where these new loads might appear on these circuits due to kind of California's climate goals and state goals around electrification. And what we found was that there are many, many circuits that kind of don't have the room to accommodate this new load. And so what that means for the electrical system is that the utility kind of has to go in and essentially upgrade these circuits, kind of give them more room to be able to accommodate these new demands on the grid. But if you look at the historical rate at which PG&E kind of upgrades these circuits and actually sends, makes the plan for upsizing a transformer, upsizing a line, sending out crews to actually do this work, their kind of operational capacity to be able to do this is much lower than what it's going to need to be in order to be able to make these changes throughout their territory. Everywhere that there is kind of a need, everywhere that their circuits cannot actually accommodate that new increased load capacity. And so in terms of, so I think there's this kind of puzzle and question to work through in terms of, well, how do we actually do this? How do we prepare our grid for the kinds of demands that will be placed on it? I think some of those answers are going to be around conventional grid investments and performing these upgrades, maybe trying to optimize them in new ways. And I think there is also room here to have a real conversation about things like citing distributed storage from kind of a utility perspective, right? To try to create some additional capacity on their systems.
Great. Tim, looks like you're coming off mute.
Yeah, I agree completely with Anna. I mean, I think, so a lot of the studies that have been published on decarbonization all seem to imply and conclude that we need to double or triple the overall capacity of the grid in the next 25 to 30 years. So think about that for a moment, right? It's taken us 130 some odd years to get to the capacity that we have today. And now in 25 to 30 years, we could potentially need to triple that. So, I think we're at serious risk of not building enough transmission. We're always going to be behind, right? That is just going to be really, really, really hard. And so we're going to enter into a time where even if my company is wildly successful and deploys an enormous number of transmission lines in the next 2 decades, we're still going to be capacity poor. We're still going to need to pull out everything we can possibly do to extract the most amount of value out of the existing capacity that we have, as well as actively control and optimize where and when we use electricity on the demand side to, again, further optimize the use of that existing infrastructure, because we're just not going to build enough to be super comfortable.
Wow.
I want to come back to that.
Yeah.
There's an idea, I forget where I heard it, but I agree with it, and probably you do too. Consumers want cold beer and hot showers. I don't care how I get it, right? So, I can run my dishwasher. I run it every night. I could run it anytime during the night. I just want it done by the morning. But there's not an easy way for me to do that. I think there's a delay feature, but really I would be open if there was a reason to do it and a way to do it, to letting a utility, save me some money on my electric bill and say, we're going to run it at midnight every night instead of, 7 p.m. or whatever it is. Is that, why or why not is that an option going forward to kind of shift some of the demand that we see?
There's absolutely room to do kind of load management on the consumer side through some of these new demand technologies that are being discussed, and some of them are in the marketplace right now. I think there's more of a need to, like, if you were to talk to an economist about this, they would say we should be doing real-time pricing so that there's kind of this real-time modularity of that is modulating essentially when these appliances are running and being turned on. And there are regulatory challenges to actually implementing that as a pricing mechanism, and maybe I won't go too further into that. But I think there's also a really important equity issue here. Like when we start talking about smart homes, we start talking about smart thermostats, you know, like if I'm living in an apartment where I'm like not in control of my own like heating and cooling, like I'm so far away from being able to use these technologies and kind of modulate my own electricity and heat consumption in a way that makes sense. And so I think there's this tendency in the industry a little bit to say, you know, what are the cool gadgets and what can we do? And it's kind of the early adopters and you know, fancy, you know, living situations that are adopting them, pulling them in. But we really need to see, I think, the grid as really serving every sector of society and thinking about how we plan for these changes with that consideration, like really firmly front and center.
I think what you're saying more eloquently is that it's more complicated than just giving everyone a nest.
Yeah. Yeah.
The value is so diffuse, right? Like the value of any individual customer is relatively small. In aggregate, it's massive value, but it's so hard. And I think people have been trying for 4 decades at least to find economic models for rolling out efficiency upgrades and demand side management upgrades to individual customers and get the economics to work. And it's just really, really hard given at the end of the day, it's the classic cost of customer acquisition. That's really, really hard. You know, I do say one thing I'll just add is I think beyond, you know, cold beer and hot showers, we can't forget industrial and commercial customers for which electricity rates and reliability is an economic competitiveness priority. And absolutely large industrial users and commercial users pay attention to rates and locate facilities where rates are low and reliability is high. And that will always be a major driver going forward. And it brings us right back to the need for transmission capacity, right? So those regions, those cities, those states that build the capacity to be able to access low-cost renewables and keep rates low are going to be the states that win from an economic development and competitiveness perspective. And that goes nationally, internationally as well, right? So I think this is ultimately, that's where a lot of the pressure is going to be applied, is when you're not catching up and you're not getting access to those low rates, that will push and force a lot more infrastructure development to remain competitive.
I'll add one more piece of the complexity that I think we underestimate how much people do care about what is involved with their cold beer and hot showers. So there is some demand programs, right? That, to Tim's point, industrial and commercial consumers are able to interact with very easily, right? Like the price signal is happening, or they're hearing from the utility, like you need to reduce demand, right? And there's usually a monetary relationship there. And a company that I used to work for, they participated in a demand management program, but it was voluntary. And so we would get emails like, please consider unplugging your laptop, right? Because you're actually not going to put something, like people don't want a switch controlled by the utility in their home that the utility can shut off without them knowing. Right, so there's a whole sort of privacy issue here when we start thinking about that data. That's incredibly complex.
Inevitably, that would be right at the climax of whatever Netflix show you're watching. Very bad timing.
And then you go back and you have a warm beer and you're nice just go and do cold shower it, and then you become a prepper, right? And you get your own home storage and so on. I'm curious, like I wanted to go back to this capacity issue, because one of the things we think about a lot is what does energy abundance unlock for society, right? Mm-hmm. Versus like sort of managed decline, right? And I feel like not being able to keep up with the capacity is sort of on that side of things. And a couple of recent news articles have me thinking about how different countries are doing this. And I'd love to get everyone's take on like, you know, what are the things that we should be doing to, you know, to try to solve for this capacity issue, right? On the one side, you see China, they have a ton of renewables in areas where they don't have demand, so they are investing heavily on capacity, right? To be more renewable driven, right? On the other hand, story coming out of the UK recently in Financial Times that they're not going to build new homes in London for 10 years because they don't have enough capacity. So how do we make sure the US drives towards energy abundance and clean energy for climate change, and also, you know, keeps up with that? So open question to everyone.
That's a big one, Liz. That's a big one. I mean, it ties into a lot of the things we've already said, right? And it's tough to say we have to build, right? Like part of the energy abundance is that we have to build across the board, right? And be willing to um, to to figure out, right, all those generation sources, geothermal, to be continuing to push on storage too, right? I mean, solar and wind is getting harder to site and build. And then ties into energy efficiency and things like virtual power plants, right? I mean, there's this whole end-to-end issue with the grid that you highlight with that question that nobody is responsible for, right? There is no one authority that is responsible for that. And I think that's really challenging. The pace of changes, right? So you said 10 years. I'll tell you what else is going to take 10 years. So 10 years to build that, to build new housing in Britain. The Federal Energy Regulatory Commission issued an order saying that utilities had to consider essentially virtual power plants, right? They had to create a way for distributed energy.
And Liza, maybe before we get too far down, could you define what a virtual power plant is for everybody?
So a virtual power plant ties in all these sorts of things that we're talking about, right? Where essentially through sort of software and grid management, you're able to pull together different resources and present them as power to the energy market, right? So it could be rooftop solar. It could also be potentially some demand side management, right? Just the opportunity to change the demands on the grid, right? And it's virtual because it's not in one place, right? But you are able to bring all this power to the grid. That's a very loosey-goosey definition. And I welcome a firmer one if anyone has it, but I'm trying to give a big tent definition to it because I actually do think there's a lot of potential for software and hardware technology to continue to define what a virtual power plant counts as, right? And how it can participate in the energy market. But the Federal Energy Regulatory Commission, FERC, right, said the energy markets have to create a way for distributed energy resources, which could include these virtual power plants, to participate in the grid. And a major system operator in the middle of the country said, yep, we hear you, and that will be ready in 2030. 10 years to get distributed energy resources actively participating in energy markets. Like, how do you create the growth that we need in those trajectories if we don't have any of the incentives or systems in place to incorporate them and use them to their best ability?
I'll add another piece onto this capacity question because I think it's really important, and that is climate change, and specifically increased temperatures more than we have planned for, throughout the United States and globally, and on a kind of a very physical level, when temperature goes up, the capacity of electricity lines to transmit power from one place to another decreases. And so there are studies that show that, in heat waves, our existing electricity infrastructure could reduce capacity by as much as like 20% in some areas. And so when we're talking about we have to build more, we have to, create room for electric vehicles, we have to be able to incorporate these new loads. We also have to be thinking about, what is climate change doing to the infrastructure? How is it creating additional congestion and bottlenecks? And we have to figure out how to plan for that uncertainty in order to be able to serve those loads.
One thing Liz and I were talking about before the call was, if you think about a city like Miami, especially maybe a couple of years in the future, you're going to have more hurricanes, more flooding. When you think about something like, do you build above or below ground power lines? How do you think about that? What is the answer?
I'll jump in with a very simple answer, right? I mean, it comes down to anticipated failure rates and the economics and the ability to build and how fast you can build. And there's not going to be one universal right answer, right? If I can build 4 overhead lines for what it's going to cost to build a single underground line, maybe I come out better overhead if I assume not all 4 of them are going to fail simultaneously. But obviously in the severity of storms that we're seeing, especially in those areas that are directly in line with a lot of those severe storms, you are going to see a lot more infrastructure being underground for that resiliency and reliability perspective. And that's absolutely necessary.
I think that's also, goes back to that distribution versus transmission challenge. When we think about the grid sort of along that spectrum, there are different issues. And in some places, it's a lot easier and faster to make the argument for undergrounding distribution. It's more local, so it's very clear who is absorbing that cost. It's also easier to fix because your technicians are right there, right? Who is managing your distribution grid is right there. In transmission, you've got longer distance to try to figure out. You're also, I mean, we've all lived in cities, they're constantly being dug up, right? So getting access to a line is a lot easier because you've got tons of infrastructure underground, right? So sure, you've got to call before you dig, but you're going to be digging, right? And so there's a little bit more kind of regularity and comfort and clarity on costs too when we think about cities. The city of Pittsburgh, where I did my PhD work, right, their distribution lines are all undergrounded. Undergrounding transmission is just it's a very different mentality, right? You are digging up likely new land. I've seen some proposals to bury in highway rights of way, so at least it's pre-disturbed and you have some knowledge of the land, but you're still going over long distances. And if something goes wrong, you've got a higher capacity issue on your hand than a distribution system where you can reroute to other power.
There does seem to be growing interest overall in finding innovations that can reduce the cost of underground transmission as well as distribution. That's a super important area. I don't think there's any single silver bullet technology that's likely to come, but you are going to see a lot of innovation in that area that I think is important to track.
All right, I'm going to do an audience question now, and I encourage other folks in the audience to please submit their questions. This one's coming at us from the Netherlands. So instead of storage, what do you guys think about switching off non-core demand and compensating for it? So we talked about the idea of these like voluntary programs, please unplug your laptop, but what about the other end of it, right? Of actually providing an incentive on the end, right? What are the ideas there to try to diminish demand and incentivize?
So we've had some of those for a long time. There are industrial and commercial demand response programs that pay incentives for curtailment at certain times of day or certain number of times of the year, that sort of thing. There have been more and more attempts to do the same at residential level in different geographies with different levels of success. I certainly know that here in Massachusetts, there is a utility program that I've signed up for where they can curtail use or adjust my thermostat, in certain periods on the hottest days of the year. It is a relatively small proportion of overall energy use today. So there's absolutely room for expanding those programs.
Great. One more from the audience, and this is one that, open to everyone. So talking about heavy industry future energy needs and the idea about differentiating between energy molecules and energy electrons. Right. So, the role of green hydrogen and stuff like that. And we've actually, spent a decent amount of time looking at different hydrogen technologies here and sort of things like that. Right. I think it's great for industrial heat for steel and so on. But, how do you guys think about, we're seeing things like on the data center side, there's a partnership for Fervo to create geothermal energy for Google data centers. Right. Do you think we'll see more of that going forward? I guess open-ended. Thoughts on the industrial side of energy demand.
Yeah, I think absolutely. We're going to see more of that. And it speaks to some of the changing business models that we were talking about earlier on the top of the hour, right? That there's so much more kind of access and understanding and need, right? You see these industrial customers with different sort of pressures, right? And a place like a Google data center sort of has a long-term need for power and the market ability to get it. And so I do think we're going to see more of that. I think what's interesting is in some ways we actually see a lot of that, right? Which I think you were referencing too, Liz, and that plenty of industrial customers also generate their own electricity on site, their own power on site as it is, right? And so we're going to see just that happening more at the electricity level, where a lot of times that power doesn't have to get converted to electricity to be used. And now it's just going to be happening more in the electricity space. And I think that's it's just really going to change how the system gets used because the power still has to get there, right? There's now different people trying to buy on to electrons, which we're not actually tracking, right? So it really changes how, what the pressures are on the folks who are managing and monitoring that actual flow when the purchasing is sort of happening outside of the system.
In my mind, it really just comes down to the economics, right? So there are several miracles that you have to overcome to get to very, very low cost, widespread, ubiquitous availability of things like hydrogen. And there are several miracles you have to overcome to be able to expand the grid as fast as we would need to expand the grid to electrify industry, plus more innovation on the actual electrification process itself for a lot of those processes, right, that are inherently heat-based. So it's anybody's guess which of those innovations are going to come true. And we need at least one of them. So we've got to be pursuing all of them at this stage.
I think we're just about at the top of our hour. I wanted to end on kind of a hopefully fun question. So 120 years ago or so, Edison and Tesla were fighting over whether or not we should use AC or DC as kind of the standard. So I'll frame this question as kind of a pick your fighter, Tesla or Edison. Granted, you have a little bit of hindsight here. But Anna, I'll start with you. Do you like, if you could go back and make that choice again, what would you go with?
It's a really good question. I think there's room for both, and maybe that's the kind of diplomat in me answering this question.
Sound like an
there's
investor,
room for both.
preserving optionality.
I do think there's room for moving towards more DC in closer to load. I mean, in incorporating batteries, more distributed energy resources throughout the grid, throughout the distribution grid, to really accommodate some of these new loads that we don't have the capacity for today. To me, it's like the implementation and the regulatory pieces kind of really start blinking really brightly when I'm saying that. So I think we need to be thinking about both. I think we need to be thinking as we set kind of new standards and new ways of moving forward, like what is really the right kind of solution, and be okay with maybe having that solution be different in one place versus another, or at one scale of the grid versus another scale.
Thank you. Liza, I'll go to you next. AC or DC? What do you choose?
That was impressively diplomatic, Anna, as you said. Even with the hindsight and even with getting my dissertation on HVDC, I would still say 140 years ago, it was AC. I mean, the technology that Edison needed was not invented until the 1940s, right? He couldn't be efficient in transmitting electricity, and AC could be efficient. I think what's important now, to Anna's point about how we move these things back together, is now the technology isn't the problem, right? So we need to be opening up sort of this regulatory space to come back to getting our least cost and most competitive things in the system. But it was AC 140 years ago, no question.
All right, Tim, bring us home.
I agree completely. I mean, the AC transformer was a magical device, right? It allowed you to get to high voltage with low losses because you're reducing the current and transmit over long distances, right? And that the technology to do the same with DC didn't exist at the time. I do think we will see more and more DC in the future, but that AC the importance of AC transformers can't be understated.
Wonderful. Thank you guys so much for joining us today. This has been fantastic. A ton of new learnings. Brad, do you want to say anything else to?
No, I was just going to say thank you, especially to the panelists, to the audience, Liz, to you. This has been a lot of fun. I feel like coming out a lot smarter, and definitely know who I'm picking in my my Edison versus Tesla fights in the future.
Thank you all so much.
Bye.